Have you ever really thought about gravity? Like what it actually is doing out there in the cosmos? Or maybe why sometimes time feels like it's dragging or flying by? Well, it turns out there might be more to that than just feeling.
Hmm.
Today, we're doing a deep dive into something pretty fundamental. Albert Einstein's theory of relativity. It's this amazing framework that didn't just tweak our understanding of the universe, it completely flipped the script on reality itself.
It really did. And to appreciate just how huge that flip was, you kind of have to picture physics back in the late 1800s. It was Newton's world, basically.
Isaac Newton, yeah. Apples falling, planets orbiting.
Exactly. His laws of motion, his universal gravitation, they were incredibly successful, explained so much very accurately. But cracks were starting to show. By the 1890s, scientists kept bumping into weird experimental results, things that just, well, didn't quite fit Newton's neat, absolute picture of space and time.
And one of the biggest head scratchers was light, right?
Oh, definitely. Light was a major puzzle.
James Clerk Maxwell, back in 1865, he'd figured out light travels at a constant speed in a vacuum. You know, that mind-boggling 300,000 kilometers per second, or what, 186,000 miles per second.
That's the one, a cosmic speed limit.
But here's the really weird part, and where it breaks your intuition. Experiments, like the famous Michelson-Morley one in 1887, they kept showing light always travels at that exact speed. Always. No matter how fast you, the observer, are moving.
Right, which makes no sense from everyday experience.
Exactly. Like if you're on a super fast train and you shine a flashlight forward, you'd think the light speed would add to the train speed, wouldn't you?
Logically, yes, but nope.
You'd still measure the light zipping away at 186,000 miles per second. It was this paradox that nobody could really explain. And that's where Einstein comes in.
That's precisely the stage. In 1905, this young guy, Albert Einstein, he was just 26, working as a patent clerk, believe it or not, publishes this absolutely revolutionary paper.
Not exactly your typical physics professor background.
Not at all. And this paper laid out his theory of special relativity. It specifically dealt with objects moving at constant speeds, particularly when you get close to, light speed. And it just fundamentally challenged everything we thought we knew about space and time being absolute.
Okay, special relativity. And it's built on just two main ideas, these postulates, right? They sound simple, but I gather the implications are huge.
Deceptively simple, yeah. But profound.
So the first one, the laws of physics are universal. What does that mean in practice?
It basically means the rules don't change just because you're moving. The fundamental laws, how gravity works, how electricity and magnetism behave, all that stuff, they're the same for everyone, everywhere, as long as you're moving at a constant speed, not accelerating, just cruising along.
So if I drop a ball in a spaceship moving steadily, it falls just like it does here on Earth.
Exactly. Or if you use magnets, they'll work the same way. There's no special master viewpoint in the universe, no preferred frame of reference, as physicists say. Your couch is just as valid an observation post as a rocket ship, physics-wise.
Okay, that makes sense. A big shift from thinking maybe there was some absolute rest frame. And the second postulate, this is the light speed one again.
Yes, the second one brings us back to that puzzle. The speed of light is constant, and this is the real mind bender.
It means, like you said, no matter how fast you're going, light speed in a vacuum is always measured as the same number, that 300,000 kilometers.
Always. Imagine you're in that spaceship again, this time flying at, say, half the speed of light, and you turn on your headlights.
Right.
You might think, okay, the light should move away from me slower because I'm already moving so fast. But nope. You, inside that ship, will still measure that light beam racing away from you at the full 300,000 kilometers per second.
It just feels wrong.
Yeah.
But you're saying experiments confirm this.
Countless experiments, incredibly precise ones. It absolutely defies our everyday common sense, which is built on speeds much, much slower than light. But it's how the universe actually works.
Wow. Okay, so these two ideas, universal laws, constant light speed, they seem simple enough on the surface, but you said they lead to some wild consequences.
Oh, yeah. This is where reality starts to feel seriously weird. The first big consequence, and maybe the most famous, is something called time dilation.
Time dilation. Sounds like science fiction. What is it?
It's the idea that time, well, it doesn't tick at the same rate for everyone. It's not absolute. Your experience of time literally depends on how you're moving relative to someone else.
Wait, so time can actually slow down or speed up? It's not just a feeling, it's physical.
It's absolutely physical.
Right.
Real. If you move very, very fast, we're talking speeds approaching the speed of light, time will genuinely slow down for you compared to someone who's, say, standing still back on Earth.
How could that even work? Give me an example.
Okay, imagine you blast off in a super fast spaceship, maybe traveling at 90% the speed of light. You go on a trip. For every hour that passes for you on the ship, maybe 2 hours pass for your friend who stayed home.
So I come back younger than them, relatively speaking.
Exactly. You would have literally aged slower because your time ran slower due to your speed. And this isn't just theory, it's been measured.
Measured. How?
Famously, back in 1971, scientists flew extremely precise atomic clocks on airplanes zipping around the world. When they landed and compared those clocks to identical ones that start on the ground,
Let me guess the airplane clocks were slightly behind.
they were, just by tiny fractions of a second because planes are much slower than light speed, but it matched Einstein's predictions perfectly.
Wow.
And it happens for astronauts on the International Space Station, too. They're orbiting at about 28,000 kilometers per hour. Over a 6-month mission, they age about 0.007 seconds less than us down here. Tiny, but real.
That is genuinely mind-bending. It makes you wonder what now even means across the universe.
Okay, so time gets stretchy. What about space? Does that get weird, too?
It does indeed. Time dilation has a twin, kind of. Length contraction.
Length contraction, so things get shorter.
Objects appear shorter, specifically in the direction they're moving when they travel close to the speed of light, as seen by a stationary observer. Let's take that 100-meter spaceship again.
Okay, 100 meters long when it's parked. Right. But if it zooms past Earth at 90% the speed of light, observers on Earth wouldn't measure it as 100 meters long anymore. They'd measure it as being only about 44 meters long.
Whoa. Does it feel shorter to the people inside?
No, that's the key. For the people on the spaceship, everything seems normal. Their ship is still 100 meters long to them. It's only shortened from the perspective of the outside observer watching it fly by at relativistic speeds.
So space itself is relative too.
Exactly. It happens because space and time aren't separate things. They're woven together into this four-dimensional fabric, what we call spacetime. What one person measures as purely distance, someone else moving relative to them might see as a mix of distance and time. They're interconnected, like two sides of a cosmic coin.
Okay, space-time. Time dilation, length contraction. This is already twisting my brain. But there's one more really famous bit from special relativity, isn't there? The equation everyone knows.
Yes. The superstar equation, E-mcdi.
Energy equals mass times the speed of light squared. What's the deep meaning there?
The really deep insight is that energy, E, and mass, M, aren't just related. They're fundamentally the same thing. They're two different forms of the same basic stuff. Mass is like, well, incredibly concentrated energy.
And energy has mass.
In a sense, yes.
Yeah.
And that c squared, the speed of light times itself, is the conversion factor. Since c is a huge number, 300,000 kilometers, squaring it makes it astronomical.
Right, so c squared is massive.
Which means even a tiny, tiny amount of mass is equivalent to a colossal amount of energy, E.
And that explains, like, nuclear power and stars.
Precisely. Stars shine because they're constantly converting a little bit of mass into a tremendous amount of energy through nuclear fusion. Nuclear bombs work on the same principle, just in a much more uncontrolled way.
And does E-mc-MEL also explain why you can't reach the speed of light?
It does, because as you try to accelerate an object faster and faster, its kinetic energy increases. And since energy and mass are equivalent, its effective mass also increases. As you get closer to the speed of light, your mass approaches infinity.
And you'd need infinite energy to go any faster, which is impossible.
Exactly. The universe has this built-in speed limit enforced by the very nature of mass and energy.
Okay, so that's special relativity. Constant speeds, time dilation, length contraction, it's mind blown. But you mentioned Einstein wasn't done. He had more up his sleeve, something about gravity.
Absolutely. Special relativity was groundbreaking, but it only dealt with constant motion. The real universe is full of things speeding up, slowing down, changing direction, acceleration. And crucially, it didn't explain gravity. Newton's gravity was still this mysterious force acting at a distance.
Right, the invisible rope pulling things.
Einstein felt that wasn't the whole story. So over the next decade, he worked on an even bigger theory. In 1915, he unveiled his masterpiece, the theory of general relativity.
General relativity. So this one tackles gravity and acceleration.
Yes. And it threw out the idea of gravity as a force altogether. Einstein proposed something much more, well, geometrical.
Geometrical. How can gravity be geometry?
Remember space-time, that four-dimensional fabric we talked about with special relativity.
Yeah, space and time woven together.
Well, Einstein's big idea in general relativity was that massive objects like planets, stars, galaxies don't just sit in space-time, they actually warp it, they curve it.
Warp space-time, like bend it.
Exactly. Think of space-time as a giant, stretchy trampoline. If you put nothing on it, it's flat. But if you place a heavy bowling ball, say, representing the sun, onto the trampoline.
It creates a big dip, a curve around the ball.
Right. Now, if you roll a smaller marble, maybe representing the Earth nearby, what happens?
It doesn't roll straight anymore. It curves around the dip caused by the bowling ball. It might even start circling it.
Precisely. And that, in a nutshell, is Einstein's view of gravity. Gravity isn't a force pulling the marble, Earth, towards the bowling ball, sun. The Earth is simply following the curve, the warped path, in space-time created by the sun's mass. Planets orbit stars because they're following the straightest possible path through curved space-time.
So gravity is the curvature of space-time caused by mass and energy. That's
Yeah.
incredibly elegant.
It is, isn't it? A complete rethinking of gravity.
But okay, that's a beautiful idea. The trampoline analogy helps. But how did Einstein prove it? How do you test something like warped space-time?
Well, like any good scientific theory, general relativity made specific, testable predictions. And confirming these predictions is what really cemented its place.
What were some of the key tests?
One of the first and most dramatic predictions was about light. If massive objects warp spacetime, Einstein reasoned, then even light should follow those curves. So light passing near a massive object like the sun shouldn't travel in a perfectly straight line.
It should bend.
It should bend, yes. And he calculated exactly how much it should bend. This was a wild prediction back then.
How could they possibly measure that? You can't see stars near the sun normally.
Exactly. You need a solar eclipse. In 1919, the astronomer Arthur Eddington led expeditions to observe a total solar eclipse. During the darkness, they could photograph the stars right next to the eclipsed sun. They compared those positions to photos of the same stars taken months earlier when the sun was elsewhere in the sky.
And did the starlight bend?
It did, and by the exact amount Einstein's general relativity had predicted. It was a stunning confirmation, made headlines everywhere. That's really what made Einstein a global superstar overnight.
Incredible. Just from observing starlight during an eclipse, what else did general relativity predict?
Another key prediction is gravitational time dilation. We talked about time slowing down due to speed and special relativity. Well, general relativity says gravity also slows down time.
So time runs slower where gravity is stronger.
That's right. Clocks closer to a massive object deeper in a gravitational well, you might say tick slightly slower than clocks further away, where gravity is weaker.
Like clocks on the ground versus clocks in orbit.
Exactly. Clocks on the surface of the Earth tick ever so slightly slower than identical clocks on GPS satellites way up in orbit, where Earth's gravity is weaker.
Is that difference significant? Does it matter?
Oh, it absolutely matters. It's crucial for GPS to work accurately. GPS satellites need incredibly precise timing. If their systems didn't constantly account for both special relativistic time dilation due to their speed and general relativistic time dilation due to being in weaker gravity, your GPS location would drift off by miles within just a few hours.
Wow. So that map app on my phone is constantly doing Einstein's relativity calculations.
It absolutely is. Without correcting for relativity, GPS would be useless. It's a daily life application of these seemingly abstract concepts.
Okay, bending light, gravitational time dilation. Any other big ones? I feel like I heard about something more recent, too.
Yes, perhaps the most spectacular confirmation, and one Einstein himself wasn't sure we'd ever detect, was gravitational waves.
Ripples in space-time itself.
Exactly. The theory predicts that when really massive objects accelerate violently, like two black holes spiraling into each other and merging, or neutron stars colliding, they should send out ripples, disturbances, propagating through the fabric of space-time at the speed of light, like waves spreading out from a stone dropped in a pond.
And we've actually detected those.
We have. In 2015, the LIGO experiment, these incredibly sensitive L-shaped detectors, made the first direct detection of gravitational waves. They heard the chirp signal from two black holes colliding over 1 billion light years away.
1 billion light years. That's staggering.
It was a monumental achievement. It didn't just confirm another prediction of general relativity.
Yeah.
It opened up a whole new way to observe the universe. We can now listen to cosmic collisions, not just see them with light.
Amazing. And you mentioned black holes merging. Black holes themselves are a prediction of general relativity, right? Probably the weirdest one.
They are certainly one of the most extreme and fascinating predictions. General relativity allows for situations where gravity becomes so incredibly strong that it overwhelms everything else.
So what exactly is a black hole, according to the theory?
It's a region of spacetime where gravity is so intense that nothing, not even light, can escape once it crosses a certain boundary. That boundary is called the event horizon. Inside, the theory predicts all the mass collapses down to an infinitely dense point called a singularity. The quantum mechanics probably has something to say about what really happens at the singularity.
So it's like the ultimate gravitational trap, an extreme warp in space-time.
The ultimate work, yes. It basically pinches off a region of space-time from the rest of the universe, at least in terms of things getting out.
And we know these aren't just theoretical constructs anymore. We've seen them.
Well, we can't see a black hole directly, obviously, because light can't escape. But we can see its effects on things around it, stars orbiting an invisible point, gas getting superheated as it falls in. And then the big breakthrough came in 2019.
Right, the Event Horizon Telescope.
Exactly. This global network of telescopes managed to capture the first ever image of a black hole shadow. They observed the supermassive black hole at the center of the galaxy M87, and the image showed this dark central region, the shadow, surrounded by a bright ring of glowing gas swirling around the event horizon.
And it looked just like the theories predicted.
It looked remarkably like what general relativity predicted we should see, a glowing ring of light bent around the edge of the abyss. So yes, black holes are real, they're out there, and they represent gravity working in its most extreme form.
Okay, so we've gone from Newton through special relativity's time dilation and EMC fiat to general relativity's warped space-time, bending light, GPS, gravitational waves, and black holes. It's a lot.
Yeah.
But you might be listening and thinking, okay, cool science, but does it really affect me?
Yeah.
You mentioned GPS. Are there other ways relativity touches our lives?
There are, maybe more subtly. We already hit GPS, which is huge. But also, think about medical imaging. Techniques like PE scans, positron emission tomography rely on particle accelerators.
Right.
And the design and operation of those accelerators, dealing with particles moving close to light speed, absolutely have to take special relativity effects into account. So, indirectly, medical diagnostics benefit.
Huh, interesting. I wouldn't have connected those.
And then, on the grander scale, general relativity is literally the foundation of modern cosmology. Our entire understanding of the Big Bang, the expansion of the universe, how galaxies form and cluster, dark energy, it all rests on Einstein's description of gravity and space-time. It's the rule book for the cosmos.
So it shapes our understanding of everything from subatomic particles and accelerators to the entire universe's history and fate. That's pretty far-reaching.
It really is. And beyond the purely scientific or technological impacts, Einstein's ideas fundamentally changed how we as humans perceive reality.
Oh, so?
They showed us that concepts we thought were absolute and fixed, like the steady ticking of a universal clock or rigid, unchanging space, are actually fluid, relative, dynamic. Your experience of space and time depends on your motion and your gravitational environment.
That's a profound shift in perspective.
It is. And that shift has seeped into our culture. Think of artists like Salvador Dali and his melting clocks. That's a very direct visual riff on the relativity of time. Or countless science fiction stories exploring time travel, wormholes, warp drives concepts, often inspired, even loosely, by the possibilities relativity opened up. Think of Interstellar and its depiction of time dilation near a black hole.
Right. Where the crew ages only hours while years pass back on Earth.
Exactly. Relativity didn't just change physics, it reshaped our imagination about what the universe could be. It showed us it's a much stranger, more wonderful, and more interconnected place than we previously thought.
It's not the complete picture, is it? You mentioned earlier that general relativity and quantum mechanics don't quite mesh.
That's right. That's arguably the biggest challenge in fundamental physics today. General relativity is brilliant at describing gravity and the large-scale structure of the universe, stars, galaxies, the cosmos itself. Quantum mechanics is equally brilliant at describing the other forces and the behavior of matter at the smallest scales, atoms, particles.
That they don't work together.
They speak different languages, essentially. General relativity is smooth, continuous space-time. Quantum mechanics is inherently fuzzy, probabilistic, dealing in discrete packets, quanta. When you try to apply both in extreme situations, like inside a black hole at the singularity, or understanding the very first moments of the Big Bang, the equations basically break down. They give nonsensical answers, like infinities.
So we need a new theory, a theory of everything.
That's the holy grail, yes. A theory of quantum gravity that can successfully unite Einstein's description of gravity with the quantum rules governing everything else. Physicists are working on candidates like string theory or loop quantum gravity, but we're not there yet. It's a huge puzzle.
And there are other cosmic mysteries too, right? Things that don't quite fit even within general relativity as we know it.
Oh, absolutely. The big ones are dark matter and dark energy. Observations of galaxies rotating too fast and the universe's expansion accelerating tell us that the ordinary matter and energy we understand, the stuff that makes stars, planets, us, only accounts for about 5% of the total stuff in the universe.
Only 5%. What's the other 95%?
Well, about 25% seems to be dark matter, some kind of invisible matter that interacts gravitationally but doesn't seem to emit or absorb light. And a whopping 70% seems to be dark energy, this mysterious pressure causing the universe's expansion to speed up.
And these don't fit into Einstein's equations easily.
We can put terms into Einstein's equations to represent them, but we don't know what they fundamentally are. Are they new particles? New forces? Or is it possible that general relativity itself needs modification on cosmic scales? These are major open questions that drive a lot of current research in physics and astronomy.
So even a century later, Einstein's theories are still at the heart of the biggest questions we have about the universe. Which brings us back to the listener. Why should you really care about all this abstract, century-old physics? I think it's because it's fundamentally about us, about our place in this vast, strange cosmos. Relativity tells us the universe isn't just a static stage. It's dynamic, interconnected, and frankly, full of surprises we're still uncovering. It's a story about human curiosity pushing the boundaries of knowledge.
I agree. And on a practical level, as we discussed, it's already woven into technologies you use, like GPS, and impacts fields like medicine. But beyond that, there's just something thrilling, isn't there? Knowing that time isn't fixed, that space can bend, that mass and energy are the same thing. It reveals the universe as this incredible playground of physical laws waiting to be explored.
So to wrap up our deep dive today, we journeyed from the puzzles facing 19th century physics through Einstein's 1905 special relativity, giving us time dilation, length contraction, and the iconic E-CR all the way to his 1915 general relativity, which painted gravity as the curvature of spacetime itself.
Explaining bending light, gravitational time dilation, predicting gravitational waves and black hole.
Exactly. Einstein gave us a completely new lens through which to view the universe. It's this epic story of bold ideas, tough experimental tests, and a legacy that's still profoundly shaping science and even our culture today.
And maybe the final thought to leave you with is this. Because of Einstein's insights, we know the universe is fundamentally stranger, more flexible, and more wonderful than we might have otherwise guessed. It's a constant reminder that there are deep truths about reality still waiting to be discovered. And what sounds like pure science fiction today, well, it just might be the science fact of tomorrow.